Suppose two classes take a statistics test. And in class A, the grades on the test are 72, 73, 75, 75, 77, and 78. Then class B, the test scores were 47, 59, 75, 75, 94, and 100. If you wanted to know how the people did in the class, you might think, well, let's use those measures of center we talked about, the mean, the median, and the mode. Well, if you calculate those for class A, you get that the mean is 75, the median is 75, and the mode is 75. If you calculate those for class B, you get that the mean is 75, the median is 75, and the mode is 75. So if you just look at the measures of center, that can leave out a lot of information, because here, those two classes had all the same measures of center, but there's definitely some important differences between the two sets of data. If you look at class A, everybody got a C. All of the data values there are close together. But by comparison, if you look at class B, there the grades are sort of all over the place. You had some people who failed, some people who got C's, and a couple of people who got A's. Basically, there the grades were very widely spread apart. So instead of just giving a measure of center, like the mean or the median, when you're describing a set of numbers, what is most often done in statistical studies is people will give you two numbers. One is a measure of center, usually the mean or the median, and then they'll also give you a measure of spread or a measure of variability, a number that tells you how far spread apart the data values are. Now, one of the more commonly used ones is what we call the range. The range is a very easy measure of spread to calculate. To calculate the range of a set, you just take the highest number and subtract the lowest number. So, for example, for class A up above, if we wanted to find the range, we would take the highest number, which is 78, and we subtract the lowest number, which is 72. And then we get 6. If we wanted to calculate the range for class B, we would take the highest number, which is 100, and subtract the lowest number, which is 47. And we would get 53. So here's something that's important to understand about measures of spread. A small measure of spread means the data values are closer together. A bigger measure of spread means the data values are more widely spread apart. And here we can see that it works. Class A had a spread of 6. Class B had a spread of 53. So that makes sense that Class B is much more spread apart than Class A, based on those measures of spread. So if you tell someone the mean is 75 for a class, they could all be really close to 75. What you want to do is give them the mean and a measure of spread. So not only do they know where the center of the data is, they also have some idea of whether the data values are all close to the center or more widely spread apart. Now let's take a look at an example of another class and their test scores. Here we've got a class where the test scores are 98, 87, 86, 95, 91, 98, 27, 88, 90, 98. So most of the test scores in that class were pretty good, a lot of A's and B's. Then there was one student here with a pretty low score. If we're finding the range in that class, you would take the highest test score, which is 98, and subtract the lowest test score, which is 27. Here we would get a range of 71 points. Now that's a pretty big number. If I tell you that the difference between the lowest and highest test score in a class is 71 points, that might make you think that the data values are pretty widely spread apart, because 71 points is a huge difference when you're talking about test scores. But in this case, everybody except that one value did really well. Everybody was pretty close together except for one unusually low value. When you have one or two unusually low or high values, those are going to be what we call outliers. Unusually high or low values that might throw off the class average. In this case, that 27 would probably pull the class average down. So here I would say the range is not really a good measure of the variability or the spread of the test scores in this class. And the reason is the 27 is the only value that's not close to the others. Everything else was pretty close together. All the other values were in the 80s and 90s, but the 27 is the only one that's not close to the others. So other than the 27, everything's pretty close. Now, one thing that you'll notice is when we were calculating the range, we used the highest number and the lowest number. We ignored everything in between. If, for example, you're talking about the average income of people in the city of Bellevue, you're going to take the difference between the highest income, which is going to be some really huge number, and the lowest income. And you're going to ignore all of the data values in between. So I don't know how many people live in Bellevue. Let's say it's 100,000 people living in the city of Bellevue. You would be ignoring 99,998 of the data values and only getting information from 2 of them. So because the range only gets information from 2 data values, and a lot of times people want to get information from all the data values, something that's used much more often in statistical studies is what we call the standard deviation. Now, in this course, we're not going to go over how to calculate the standard deviation. That is definitely something that you would calculate if you get into an actual statistics course. In this class, what I want you to be able to do is to interpret the standard deviation and explain what it means. And this paragraph really summarizes what you want to think about that. Basically, the standard deviation tells you if the data values are close together or spread apart. A big standard deviation means the data values are really widely spread apart with a lot of variability and spread. A small standard deviation means the data values are closer together. So if you look back at Class A and Class B up above, one of those has a standard deviation of 18.3 and the other has a standard deviation of 2.1. So the higher standard deviation would go to the class that is more spread apart. The smaller standard deviation would go to the class that is closer together. So remembering those scores from before, Class A, the values were closer together. Class B, the values were widely spread apart. So in this case, Class A would have the smaller standard deviation, and Class B would have a bigger standard deviation. So the 2.1 is going to have to go for Class A, and the bigger standard deviation of 18.3 would go to Class B. So sometimes what I'll do is I'll give students a type of data value. I'll tell you what the standard deviation is, and I'll ask you if the data values are close together or spread apart. It's important to compare or to consider the type of data value you're talking about when you're answering those sorts of questions. For example, if I tell you that a data set has a standard deviation of 5.3, just from knowing that, you can't tell if they're close together or spread apart. If you're talking about, say, temperatures of patients in a doctor's office, and there's a standard deviation of 5.3 degrees, 5.3 degrees makes a huge difference. So those would be very widely spread apart. But if you're talking about, say, distances traveled on a cross-country road trip, and the standard deviation is 5.3 miles, on a cross-country road trip, 5.3 miles is practically nothing. So there, the distances would be very close together. So here's another example that's described. Let's say we have 2 sets that both have a standard deviation of 10. Well, if you're studying heights of children and you get a standard deviation of 10 inches, There we would say the data values are spread apart, because when you're talking about heights of kids, 10 inches makes a big difference. But let's say you're studying prices of cars and the standard deviation is $10. When you're talking about prices of cars, $10 doesn't make much difference at all. So there you would say the data values are very close together. So when you're trying to determine if a data set is close together or spread apart by analyzing the standard deviation, think of the type of data values you're talking about. If the standard deviation makes a big difference for that type of data value, then they're spread apart. If the standard deviation makes less of a difference, then the data values are closer together. Another type of measure that we're going to talk about is a measure of position. In a statistics class that's a full quarter class, you might study what are called percentiles. We're going to study just part of that, what are called the quartiles, which divide data into quarters. The first quartile, which we're usually going to abbreviate Q1, is above the first quarter of the data. The second quartile is above half the data, and the third quartile, which we'll call Q3, is above 3/4 of the data. So basically, they split the data up into quarters. Now, one of those quartiles is the same as the median, right in the middle of the data, and that's Q2. If it's above half the data, then it's right in the middle, so quartile 2 is the same thing as the median. Now there's a little bit of a typing error in the next part. Where it says Q2 on that next line, it should say Q3. So a lot of times quartiles are given as part of what's called the 5-number summary of a data set, where the numbers are the minimum or the lowest data value in your set, your quartile 1, the median, which remember is the same thing as quartile 2, and then quartile 3 and the maximum. You might have a list of 5 numbers that's what's called the 5-number summary. And that actually gives you a lot of information about the spread of the data. Here's an example. Suppose the 5-number summary for the sale price of all used iPhone 5 units on eBay during February was $40, $160, $195, $250, and $395. So that means that the smallest sale price was $40. The first quartile is $160. The second quartile, or the median, is $195. The third quartile is $250. And the highest sale price was $395. Now, we're going to answer some questions about percents. When you're using the 5-number summary or the quartiles to answer questions about percents, there's always 25% of your data between the minimum and the first quartile. There's also 25% of your data between the first and second quartile. There's 25% of your data between the second and third quartile, and 25% of your data between the third quartile and the maximum. So let's say we have this question that says, what percent of iPhone 5 units sold for less than $160? 160 is right here. Less than that is 1/4, 25% of our data. So that's our answer. If we get to our next question that says, what percent of iPhone 5 units sold for more than 160? Well, 160 is right here. More than that, we have 25, 25, and 25. That adds up to 75%. Or if we're looking at the next question that says, what percent of iPhone 5 units sold for between $160 and $250? 160 is right here, 250 is right here. In between those, we have 25% and 25%. Put together, that gives us 50%. So when you're given a 5-number summary, there's always 25% between each number. The minimum, the maximum, and the quartiles, there's always 25% between those numbers. Now, a lot of times a 5-number summary might be presented visually by creating what's called a box plot. A box plot starts with a number line. And if I'm making a box plot for those phone prices, our lowest one is 40, our highest one is 395. I think I might make a number line here. It makes sense usually to start a little bit lower than the lowest one and end a little bit after your last one. So here I'll go maybe 0 to 400. So we'll have 200 right in the middle, and then we'll have 100 about right there, 300 about right there. Next, what you do is above that line, you're going to put a short little vertical line for each number in the 5-number summary. So my first number, my minimum is 40. That would be about right there. Next, the first quartile of 160, that would be about right there. Next, 195 is just under the 200, so about right there. 250, right in between 200 and 300, that would be right there. 395 is just under 400 right there. Now to finish it, you start by making the box by connecting the tops and bottoms of those 3 lines in the middle. And then you finish by making the left tail, drawing a line from the center of the first mark to the box. Draw another line from the right side of the box over to that maximum line. And here we've created what's called a box plot. Now what the box plot shows me is that 25% of the data is always in the left tail of the box, 25% is in the first half of the box, 25% of the data is in the second half of the box, and 25% of the data is in the tail on the right. So the box plot is sort of a very different way than the histograms we were studying in the previous section of showing you the spread of the data, where most of the data values lie.